have a you are. Yeah, yeah. I think we were out there. Okay. It was better from Boston. Yeah. And on the weather side, no, by the England. Australia. You see. So, yes. Wait, what's this? There is stuff. Yeah. Okay. 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 That's pretty much that. Okay. So good afternoon, everyone. Uh, so welcome to the Future Ocean Forum. So you may find some state or even stick on one. It's okay. Yeah, yeah. So today we are uh, delighted to be, we are very honored to welcome invite Professor Neil Hobart from the University of Tasmania to give a talk here. Uh, so I would like to take this opportunity to give an introduction to him. Professor Neil Hobart is a professor of ocean and climate dynamics at the University of Tasmania. His research focus over the past 10 years has been on understanding marine behavior. I think if somebody here who are interested in marine behavior should know his name, right? Today you have a chance to meet him. I I hope in the future you have a good collaboration or connection and have a good collaboration with him in the future. Okay. Um, his research, include the drivers' potential predictability and the impact of marine behavior. He is currently a chief investigator of the ARC Center of Excellency for the Weather of the 21st Century. So you may know ARC. ARC is the Australian Research Center. Yeah, like I think like the NIFLC. Yeah, yeah. He co-leads an international working group on marine behaviors and is a member of the important program worldwide clever research focused on marine behaviors in the global. He previously led Australia Climate Change Adaptation Research Network for Marine Biodiversity and Resources, which is one of the 8 national climate change adaptation research facilities, right? Adaptation network. from 2009 to 2013. Yeah, this project. He is a fellow of the Australian Meteorological and Oceanographic Society. He also previously served as the, president of the International Commission on Climate, ICCL. We have a long, yeah. At that time, I'm a secretary general of that. Yeah. Now he's a former president of that. Yeah. Uh, he is associated editor of the Journal of the Southern Hemisphere Earth System Science. Neil has been uh, this is English name, Clarivate, right? Clarivate. You know what is Clarivate in Chinese? 科瑞维安。OK，听到科瑞维安。OK， Clarivate 因为咱们会评选科瑞维安高费敏学者。There is a Clarivate highly cited research for the past 4 years, and is identified on the Reuters 路透社啊 Reuters list of 1,000 most influential climate scientists. Okay, so I think through this brief introduction, Neil a little bit. I hope in the future you can contact with him. And today, the theme of his talk today is exploring and understanding marine heat waves. Now, let's warmly welcome Professor Neil Hoberg with a round of applause.
Thank you very much, Professor Lee. We have a long association together, and it's really a pleasure to be here, to be invited by you and your academy to give a host platform, and also to the College of Ocean Atmospheric Sciences for co-hosting this seminar. I've had a wonderful time here at OU. I've been here since last about 1.5 weeks now here. And I've primarily been teaching here. Some of the students in my class are here. I can see their smile faces. Yeah, well, let's talk about marine heat waves. So you can hear me all good? So I thought I'd take you on a little bit of a journey on how we, I guess, started to understand marine heat waves. So I'll talk about some of the past research and how this all got established. And then I'll say some words about some of the recent research, and it will just be very short snippets of information about some of the work that's been undertaken in my group. So it all started, I guess, really, you can see here on this side here, the language of marine heat waves is really only 15 years old, okay? So in 2010-11, this big temperature, you can see, extreme event happened off Western Australia. And Alan Pearce, who led, I guess, this report here, and others in Western Australia, called it a marine heat wave, right? I mean, we've had marine heat waves in some sense for ever, right? Because they're naturally occurring, but they're also changing under climate change. But this language around marine heat waves is more of a persistent, a prolonged, large-scale event really started to evolve after that time. And that got us interested. In particular, colleagues in University of Western Australia were looking at the devastating consequences of that event in 2011. The macroalgae, or the kelp in particular, particularly off Kalbarri, off Western Australia, basically died, okay? And they observed this large-scale mortality event of kelp. Also, up further north, they noticed that there were seagrass that was dying, about 1/3 of the whole of the Big Bay up there There were fish that they hadn't seen before, coral bleaching is going on, and so on. So that really stimulated our interest. That really stimulated our interest to try and understand this better. So here are just some pictures to start the ball rolling. This is my lab group here. It's some of my nice, and quite a number of those faces you might even recognise. They're students from Ocean University of China that have gone on to do PhD with me and my group, which has been fantastic. But in 2015, you can see here, this group of people here, okay, some of the names you will know from the marine heatwave literature, maybe like Eric Oliver here, Thomas Wernberg, and so on, me, and so on. Got together, 15 of us, there's 14 there, one couldn't come, in Western Australia in January during a heat wave, 40 degrees Celsius, is our summer, and had a 3-day workshop to discuss marine heat waves and how to try and understand, if you like, the physical drivers and the properties of marine heat waves. So 3 papers came out of that workshop. One was on the drivers that I led, one on trends that Eric Oliver led, and the other one was on what was it? The definition with that Alistair Hobdo, with an Alistair who's called standing at the back there. Right, so those papers now have started to become seen in the literature, I guess. And this working group, what we call this working group, has really stuck together for a long time. Now, 10 years on, you can see there's 12 of us here. This one was in Western Australia, and we met in Nova Scotia in Canada, and started to focus more on the biological impact and adaptation rate. So it's a very interdisciplinary working group, right? The people there involve ecologists, they involve physical people, atmospheric scientists. So I think that's been the strength of this group, is that it's a very interdisciplinary project, right? Marine heat waves are an extreme in the ocean of temperature, but they affect marine life. And now we're moving from understanding the drivers and so on to try and understand the predictability and the impact. This is like a mosaic of marine heat waves around the world. They're not at the same time. You can see that they've got different, bit probably people in the room heard of the blob. This one here is a very, very long event. Then we've got these ones around Australia at 55. Tasman Sea in 2015-16 was seen as the unprecedented event. It lasted for like 8.5 months and caused devastating impacts to oyster, salmon, and abalone. This is the 2011 one again, then there's one in New Zealand, one in Northern Australia, then it's more like El Nino, some oscillation and so on, but extreme, so on like that. But you can see here that with the title, I've really tried to express what we've been trying to look at. We've been trying to understand the dynamics, we've been trying to understand the predictability, the projections, the hazards, and so on. So part of that initial workshop in 2015 was to develop this definition. Some people here in the room may well use it, but this is, it's loosely called the Hobdo definition because Alistair led it. But basically, the idea is that you generate a long-term climatology, climatological cycle from, let's say, 30 years of data, and it's seasonally varying. It's not just flat, it's seasonally varying. The idea behind that was because breeding success might actually happen in wintertime, and if it's too long in wintertime, it can also be a problem. You think about things like coral bleaching, and they're stressed only really in the summertime maximum. But there's parts of the ecological system that really care about whether it's cool or so. They need some relief through the winter. And so we developed a definition that's seasonally varied. And it's somewhat arbitrary. It was informed by the atmospheric scientists, the likes of Sarah Perkins, who was at the workshop, and Lisa Alexander, who's been working in the atmospheric space for some time. and they helped us to inform that they use a 3-day definition. This is a 5-day definition where you're above some threshold here, which is what we call the 90th percentile threshold, or the top 10% of value, right, for a particular period of time. Now, the point that I want to make about this particular definition is it's point-wise, right? So it's got necessarily no connection with the neighbouring point, but you could do averages within boxes. So here, for example, you could do an average in that box, an average in that box, but really it's, it takes advantage. The beauty of this definition is that it takes advantage of satellite. You can use satellite information. The NOAA OIST data is a classic one if you want to look at temperatures over time from observations anywhere on the globe and compare. You might think then, if it's only point-wise, that the information is disconnected in space and time. But in fact, it's interesting that even with that point-wise definition, you start to look at the characteristics like intensity, frequency, and duration of marine heat waves. There are patterns, right? You can see this strong pattern in intensity, then frequency here, right? This is like the whole tongue. This is like, an El Nino event, let's say, it's long duration, and which is opposite in phase, let's say, to duration. You can see duration would be long, frequency would be low. Intensity might be large. Then in western boundary current regions, you can see the intensity would be large. The duration would be low, but the frequency might be large, and so on. So there are characteristics that are in connection with the dynamic. Those patterns don't happen by chance, right? They're quite coherent and quite reflective of the underlying dynamic. Then the group later on put together this intensity concept here, which has also been widely used. And this was produced 2 years later. The motivation for that was the thought that we really want to know about how strong the marine heat waves are, how intense they are. How do we do that? Well, it's not a tropical cyclone, right? But you think about a tropical cyclone might go, or here what we'll say typhoon, could go category 1, category 2, category 3, category 4, and so on. And so there's real benefit then in understanding the intensity, a simple measure that people can relate to and use to inform their impact studies and so on. So this was developed. This is like 1 time the 90th percentile, 2 times the 90th percentile, 3, 4, and so on, right? So so we developed this moderate, strong, severe, and extreme marine heat wave category. The other beauty of this is, as the climate changes, right, there is this ongoing challenge of what baseline you choose, what baseline climatology. With a definition like this, you can add potentially categories on top as time goes on, go to category 5, 6, and so on, and think about how the marine heat waves are actually then going up into higher. Here's some examples. Okay, here's the Tasman Sea. This is that 2015-16 event that was unprecedented. And you can see just how long that event was. As an average in that box there, or here's the intensity measure, you can see it got up to category 2. In the Western Australia one, you can see in this box here, it got actually up to category 4. This was a shorter event in time, but because of the intensity of it, it was particularly devastating. And here in the Northeast Pacific, that's connected to these blob events, you can see how long and persistent this event was. So then under the driver's paper, this was published in 2019, the same group of people, this is part of that workshop. It took 4 years to come out. So we had the workshop in 2015. And over 4 years, I was a bit slow, as I am. We eventually got this paper out. And this just gives you a feeling for the scale of marine heat waves, firstly, okay, so in terms of space scale, maybe from 1 kilometre to 1,000 kilometres or more, and based on the definition, several days through to longer than a year. And then there are 2 types of, let's say, we'll call them drivers. One is the local drivers, which are coming from down here, and the primary drivers really are ocean advection, we'll say, and the heat fluxes. Then there are other processes that might feed in and cause the temperature in a region to actually heat up locally. But then there's a connection also to these remote drivers. Okay, these are modes of climate variability like El Nino southern oscillation, Indian Ocean dipole, Madden-Julian oscillation, decadal modes, and these connecting processes, teleconnection processes like Rossby waves, ocean atmosphere Rossby waves, jet streams blocking the sun. So this was just a brain, I would call it like a brain dump. We would think about what are the processes that influence these, but informed by the literature. So this just gives you a bit of a background for how it works. It's a very simple plot. Here we've got the upper ocean. We think about a mixed layer temperature tendency here. Okay, so that would be down here. So we're looking at the change in temperature with respect to time. The heating phase would be when VTDT is greater than naught. Cooling phase is when VTDT is less than naught. And you can just look at that in terms of an overall heat budget equation. So it's there. Where in the open ocean, we found that these two are probably the really key terms. And in other studies, particularly closer to the coast, the mixed layer depth can be really important, and other terms maybe. There's just a breakdown of the surface heat flux equation, and this is really what we see as the key terms, the ocean advection and the surface heat flux. And the rest we sort of put into a residual, but you can calculate every single term here if you have the information to do it. But overall, these are the two key terms. This is a paper led by Eric Oliver. It was published in Annual Review of Marine Science. And the thing I like about this figure is that it just gives you a feeling for the types of situation where you might see a temperature change that's extreme. Okay, so here we've got, let's say, a western boundary current region. You can see the vectors pushing north there are particularly large and they're smaller offshore. Here's our sea surface temperature, our isotherms pushing further north along the western boundary. Then, if it deviates in space, you can see the vectors start to move offshore, which can happen in a varying situation. You're transporting heat into a different region there, and then you can end up with an anomaly like this, right? So this could be a form of an ocean advective marine heat wave under that circumstance. In this case here, you can see what we've got is, so that was a plan view. That was looking down on the board. So this is, let's say, north latitude, and this is longitude. Now we're looking at a vertical section, okay? So this is depth down here, and this is horizontal. Here's our mixed layer depth in a let's say, an average situation. Our heat flux is whatever it is, let's say, I don't know, 150 watts per square meter, and our wind might be, let's say, 10 meters a second, okay? But it's very flat. Then along comes a high pressure cell, okay? So the high pressure comes through, calm conditions, solar radiation increases, winds drop, and it starts to look more like this. You can see there your heat flux goes up, your wind goes down, and as a result, because the winds drop, it's not pushing the mixed layer down as far, so it wants to shoal, and you're exposing this mixed layer then to greater heating, and it intensifies here. And then when you have a look at the anomalous plot, it looks like that. It's hot at the top and cooler below, where the mixed layer pushes up. So they're the local drivers, right? But then you've got the remote drivers. And this plot here just shows you some of the modes of climate variability. It's a very busy plot, and I'm not going to spend really much time on it. But just to say that in different regions around the globe, and here indicated in these little boxes there, okay, so, and they're identified on this plot here, eastern boundary current region, western boundary current region, tropic, and middle to high latitude. You can see that there are variations and different contributions of the different modes of climate variability that affect marine heat wave likelihood, we say, right? So on average, because the Hobday definition says that it's in the top 10 percentile, you would expect marine heat waves anywhere across the globe on the order of 10% of the time. So because it's at least a 5-day definition, it actually means that it's typically less than 10% of the time. You can see that whitish line is a little bit below that. But under different phases of these modes, you can see here's the positive phase, let's say, of the PDO, the negative phase of the PDO, or positive phase of the NAO, negative phase, or then what we've got there, Southern Angular Mode, Neo Madoki, and then you've got Neo 3.4 and so on. You know, I'm sure that many of you are familiar with these kind of indices. You can see the ones that are significant for the different regions that are actually influencing the likelihood. So this is an enhancement up this way, and this is a suppression of marine heat wave days under those modes. Not all of them. You can see in the western boundary current regions, the influence is very small. It's very small because those regions are very eddy rich. Okay, they're high frequency, they last long, and they're influenced by internal modes as well as external modes, but mostly, you know, internal variability. Whereas more in the eastern boundary current region, you can see it has a much bigger influence under the different phases of those different modes. And then we've got tropics, obviously influenced largely by ENSO, so you can see a lot of green and brown in there. And in the middle and high latitudes, you can see there are a lot of modes that are playing, in particular in this northeast Pacific region, that also have co-varying, if you like, influences on the marine heat wave likelihood. Then later on, we put together a perspective piece that I led, and because I was very interested in the importance of predictability for marine heat wave on, let's say, biota. So we put together this schematic that shows the drivers, if you like, on this side, and the species impact on this side. And you can see the types of drivers. Here's the local effect from, let's say, surface heat flux under a high pressure cell when the winds are suppressed and so on. You've got more solar radiation. And the other one here from ocean effects and so on. Then you've got these remote modes that are actually playing into it, and there's teleconnections that can add potential predictability. So the point about that last slide is those modes give you potential predictability. If you have a lead time scale from that, it might help you to predict them months in advance. And that's really what this paper was about, to try and understand where the potential is coming from. Because the ocean has a longer memory, that you might expect that potentially in the ocean you might have longer lead time potential predictability for ocean processes. All right, how we done? We're there. Okay, better keep looking. All right, so I'm just going to give you a quick tour of some work that we've done together in the Pacific Islands. This is the group of people here. This was motivated by colleagues at CSIRO, and they pointed out that in the IPCC there wasn't really much about impacts in the Pacific or understanding extremes in the Pacific Islands. And so with those names, that people that correspond with these names up here, we set two. We met in Apia a few years ago, and we workshopped and talked about how marine heat waves are affecting people in the Pacific. So the Pacific Island countries are among the most vulnerable in the world to climate change. And this is, I guess, quite particularly relevant to this particular academy here. I know that Professor Lee mentioned that sort of work a lot with people around the world, vulnerable people, particularly Pacific. It can significantly impact ecosystems, coral reefs, seagrass habitats, and their people's livelihoods. Ciguatera fish poisoning is one of the impacts of ocean temperature extremes that can actually cause a lot of discomfort, sickness, and sometimes death, I believe. And so, importantly, climate predictions and climate change projections are important to understand how those islands will be in the future. This just gives you a bit of a picture of the overall circulation in the region. We're talking about here, all right, the Indo-Pacific warm pool, and the region that I'm talking about primarily here is mostly south of the equator. Palau is up here, just north of the equator. I think that's north of the equator. What are we looking at there? Palau, yes, there's Palau, okay. It's in this intertropical convergence zone. It's the South Pacific convergence zone. These convergence zones are really influenced by the warm water there and the convergent winds. The three nations, Fiji, Samoa, and Palau, were largely the focus of this particular study because they were the island people who came to the workshop and worked with us on this particular project. Look. So when we think about climate extremes and climate variability, we think about the impact as well. So let's say for thousands of years past, we might see variability like this. Here's the warm extremes up here where you might be able to adapt, right? And here's the colder extremes down here. But the main point is under here, you go up into a warm extreme and you might be able to do something about it and come back. So we will see this then is enveloped as that coating range. But then as climate changes, you can see that we're pushing the envelope. We're now starting to go beyond our adaptation into this vulnerable space. And so here, what we would have normally, then this is our extremes. This is our probability density function, if you like. So this would be our average climate in here. And here are our extremes. As climate changes, you can see the hot extremes are becoming more prevalent. And so this is obviously a considerable concern. These things brought together Pacific Island people, lived experience, traditional knowledge and science to understand the impact of climatic extremes in a changing climate. There were other work going on looking at sea level rise, drought, tropical cyclones and extreme rainfall that were undertaken by other groups of people. We workshopped, we spoke to the local people, we asked them about their concerns, what they knew, what they didn't know. Of course, it was all ethics group, and tried to understand the concerns and problems that they were going through. You can see here, this is informed by that driver's paper that at least during El Nino, you can see that we've got this enhancement of marine heat wave likelihood and a suppression there during El Nino events. But in the reverse case, you can see there's a suppression here in La Nina, but it's obviously colder, enhancement of the cold front, and this is an enhancement here. So it's effectively flipped. It's not, this is actually a bit symmetric, so it's not a perfect model, but it just gives you a feeling for it. So in fact, in this region here in the South Pacific, it's actually quite complex because many of the islands sit on the cusp between this red and blue. So in here, where things can just shift around, and it's very much an imperfect predictor of the conditions that they might experience. So in Palau, here's an example of a particular impact. Here you can see we've got this marine heat wave off the northeast of Palau. Palau is a beautiful place in the Pacific Ocean. I haven't been there, but I've seen the photos and I'd love to go there sometime. And you can see that this particular event happened between July and October 1998, between the end of the 97-98 El Nino and the start of this La Nina period. So it was right on the cusp. So there's not much information there necessarily. Fiji event here, you can see that there's this warming here off the south coast. It caused fish, or resulted in fish death. Okay, so that could have been related to low oxygen water or harmful algal blooms. In this Palau event, you can see there was massive coral bleaching that occurred. But you can see it happened during the peak of the El Nino. And in Samoa, you can see here, there was also coral bleaching in Palolo Beach. This event happened off the coral coast of Fiji. And you can see this is a particularly common thing. So just to finish off now in this particular part of the talk, I just want to show you how things have changed and now how things are projected to change in the region. So here we've classified the marine heat wave from moderate, strong to severe and extreme. And you can see over the historical period there, in the moderate and strong, you can see there's an increase there from these colours to redder, corresponding to these marine heat wave days. But in the higher categories, severe and extreme, there's very little change yet. And this was reflected down here by this fraction of the ocean, that whole ocean up there, that's actually been influenced by marine heat wave changes. So you can see that the moderate and strong there is going up. Severe and extreme hasn't really done anything over that period until the recent time, but the fraction of ocean that is actually got no marine heat waves has actually gone down. But in terms of climate change projections, we rely on models, right? So projected surface temperature changes are often done according to scenarios of how many watts per square metre that we're going to actually have in our climate system in the future. And under these shared socio-economic pathways, CMIP 6 simulations under the 6th assessment report were undertaken. We're now going into the 7th cycle of IPCC, and there'll be a CMIP 7, I think, underpinning that. But under the Paris Agreement in 2015, it aimed to limit warming to well below 2 degrees and preferably be below 1.5 degrees. So economists and energy people put together these scenarios. This SFP 2.6 to 1.9, which is a low, more sustainable pathway, which are these blue lines. Then we've got middle of the road scenarios with 2, 4.5, and the fossil intensive ones, let's say 5, 8.5, and 3, 7.0. So these numbers at the end here, this 2.6 means 2.6 watts per square metre of additional, if you like, greenhouse forcing by the end of the 21st century, and this is 8.5 additional watts per square metre of heat in the system. So this one here is even the let's say the 2.6 will likely reach 1.5 degrees by 2030, but you can see that it starts to turn over and temperatures are likely to decline up to 2050. The middle scenario will reach 2 degrees by 2060 and 2.7 by 2100 projected, whereas this one, we just don't want to go there, right? I mean, it's like talking 4 to 5 degrees of warming by the end of the 21st century. What this looks like for the Pacific Island regions is like this. You can see there's a lot of red in here, obviously, but when you get down to the severe and extreme ones, you can see the severe is going from this period here, going up to, this is the SFP 2.6 scenario. There's not much going on in the extremes, but there's some warming here in the severe category through to 2060. But in the high emission scenario, 5, 8.5, you can see even the extremes are going up to maybe 25 days per year of that. So it's something that's a great concern. All right, so the messages that I just want to convey there is marine heat waves in the tropical western central Pacific Ocean region have increased in occurrence and intensity over the past 40 years, having tangible ecosystem and fisheries impacts. The projections under 8.5 would be expected to have serious implications, and adaptations of Pacific Island community, stronger, higher categories, marine heat waves may be insufficient in the future without an aggressive emission reduction. The low emission scenario will be important going forward. All right, so the last part of this talk is I just want to talk about some of the work that's been undertaken within my group, but also through previous Centre of Excellence, which is the Australian Research Council Centre of Excellence for Climate Extremes. And together with Pete Strutton at the University of Tasmania, we co-led this space here, the Ocean Extreme Research Program. You can see that there are other research programs in here. This ran from 2017 to 2024, so it finished last year. And now there's a new centre called Weather of the 21st Century, which I'm also involved in. You can see that it's a consortium of 5 universities. It was led by University of New South Wales, where Professor Santoso, who's FLIBAR here, a representative, director, Monash University, University of Melbourne, Australian National University, and University of Tasmania. These were the thematic areas of the ocean extremes we were working on through the centre. You can see there was a lot of activity. Pete Strutton, my colleague, was working largely in this space, in front and biogeochemistry, and then other people within the centre, some of which where I was working within dynamic climate modes, certain coastal marine heat wave modelling, predictability, risk. Here is a former postdoc of mine, Gabriella Pillow, who was working collaboratively with me and Andrew Fifth and Andrew Polk at ANU. We wanted to understand the role of model resolution on marine heat waves, right? If we're going to represent marine heat waves for understanding the dynamics and potential for future projections, we need to know just how representative those models are. Overall, models do a really good job, I would say. Even If we have a look at this, this is a 1 degree model. Okay, so this is, we would say, coarse. This is a 0.25 degree model or 25 kilometre scale model. Okay, so it's like eddy permitting. This is an eddy rich one, a 10th degree scale, and this is NOAA OISSC observation. Overall, you can see the pattern represented by here, by all models, is actually pretty good. In fact, you know, it's really, I think it's heartening for me to see that even the 1 degree model does a reasonably good job overall in terms of spatial patterns, which suggests that the dynamics, even with the large scale, are being represented well. The things that really matter in terms of large scale climate variations and so on. But if you dig down into the detail, you can see that the 10th degree is really capturing these things like in the retroflexion regions and so on, which this model up here just isn't really showing properly. But the other thing that you overall, you'll see that this is actually redder overall than these. So there is a bit of a bias in the model, and they tend to be weaker and longer lasting and less frequent than these observations. And this plot down the bottom here just shows the difference between the different models. This is the 1 degree model, the 25 kilometre model, the 10 kilometre model, and this is observations. And you can just see how falling short they are in terms of mean intensity. So these are the events that we've seen before. This is in our region, in the Tasman Sea. In 2015-16, we had, as I said, this big unprecedented event. You can see that the scale of it in terms of horizontal scale is quite relatively narrow compared to this one. This was an advective event. It was deemed to be that way. There was a fraction of attributable risk analysis undertaken on it, and it seemed to be much more likely due to climate change. As was this one, which was more of a top-down one from surface heat flux. You can see it's more consistent with this high-pressure cell, much broader, much shallower in extent. This is down to 200, 300 metres. This one down to about 20 metres depth. But both had quite devastating impact on fisheries and aquaculture. Another former postdoc who's now at National Oceanography Centre, Jules Kaiser, worked with me and Gabby Pillow again, Scott Bachman at National Centre for Atmospheric Research, who run an ultra-high resolution model, 1 kilometre scale. You can see here, if I ran that animation, you see it just looked like milk going around in a coffee cup. This incredible resolution, but only for a very, very short time to try and understand the role of maybe some mesoscale processes on the event in 2017-18. Remember, that was a very shallow event, right? 2017-18, and there was a weather event that came through. And for my thinking, I thought, well, you know, weather event, this will break it up, you know, 20 meters, maybe I'll just get rid of it. But it didn't. It persisted onwards. So we tried to understand that better with the hypothesis that maybe there was mixing downwards that might be just holding it there. It turns out, at least from this analysis in this paper, the sub-mesoscale didn't seem to play a big role. Might be some other work now that's trying to challenge that, but that was the finding of this paper, that it was really largely kicked off by the effective event at the start, persistent high that came over, just helped to keep it that way over time. This is other work with a full, oh, hang on, how did that go? Okay. Zoya Li, who's a graduate from Ocean University of China and UTAS. She did a PhD with me and Yugen Zhang at UTAS. And this one was just an analysis of the role of oceanic Rossby waves in potential predictability of marine heat waves. So this is an example here. You can see some SST and, well, sea level as well, moving here from east to west over quite some months, from say 70 months prior right up to here. And there was an analysis undertaken between offshore to New Zealand and then across the Tasman Sea to here. So this plot here, it's a bit complicated, but I'll just go through it fairly quickly. We've got the southward transport of the East Australian current in Sturgeon here in the blue line. And this black line is basically sea level, sea surface height, that was seen 26 months earlier here around New Zealand, that's associated with the Rossby wave planes coming into there, and the time scale then for those rocky waves, being baroclinic rocky waves at this point, to go across the Tasman Sea and potentially influence this low frequency variability of the transport of the Australian current. So you can see there that connected there with that 2015-16 marine heatwave event. The idea here is to try and understand the role of these lower frequency variations like teleconnections from oceanic rocky waves on marine heatwaves. Here's another graduate from Ocean University of China, Yuxin Wang. So Zoya Lee's moved on to Perth now, working for CSIRO. Yuxin Wang has finished the PhD with me. She's just recently graduated and she's now working at the University of Hawaii. So she's doing also very well. And here's two examples of her work. Just quickly, she used a linear inverse model here over on the left. It's a data-driven model. It has a noise component, a bit like the first autoregressive model 1, but here with spatial variability, and a deterministic component here from this dynamical operator over here. The assumptions are linear. We used a seasonally varying cyclostationary type length and tried to analyze the role of different modes of variability on predictability of the marine heat waves off Western Australia over time, and showed that with this kind of approach, you could understand that you have about 1.5 times more likely to have a marine heat wave in this region here with a positive Indian Ocean dipole. But the other thing is it's very connected, obviously, with the Pacific, and this region here is very influenced by ENSO, largely due to, let's say, La Nina. So under a La Nina event 5 months in advance, you would have about a 2.5 times more likely event of marine heat waves, and combined together about 2.8 times. So you can imagine how you might stack up with predictability over time and try to understand how that is with this type of approach. And then more dynamically, in another paper published in Journal of Climate, she used a shallow water modeling approach, reduced gravity model that I built many, many years ago to understand the role of the easterly wind extremes on forcing downwelling rocky waves, Kelvin wave down the coast into this zone here. So the punchline of this paper was just that La Nina is, you might expect to be important for marine heat waves off Western Australia, and indeed, often that's the case, but it's not a guaranteed thing. It's actually the extremes of the winds here that are more likely to cause that, and a La Nina may not actually, when a La Nina may not actually occur. So it's a necessary but sort of instant condition. Then just based on this earlier work that I was doing when we worked together on the driver's paper, you can see that with these different modes of variability, again here, as I said, you can enhance or suppress marine heat waves over various regions of the globe. Here's a pattern for El Nino, let's say, and positive DMI. And here's patterns for negative southern annular mode. You can see influencing marine heat waves in the Southern Ocean and the negative NAO here in the Atlantic. And this is just a sort of a messy color picture that shows the dominant influence across the globe. This was taken a little bit further now by another former student who's now working at the University of Bern with Thomas Frulicker, who sort of built on that work but focused more on the regions around Australia here. And the interesting thing about this work is that you can see she's added a couple of more factors, subtropical ridge high, and also the Madden-Julian oscillation. So now we're moving away from interannual drivers to more subseasonal drivers. Her focus is on subseasonal to seasonal variability. And it turns out that phase 3 of the Madden-Julian oscillation seems to have an important role in potential predictability down this part of Northern Australia. To take this a little bit further, this is Catherine Gregory, by the way. Catherine then started to understand, well, one of the things that was argued that, was that, well, El Nino tends to cause coral bleaching in the Great Barrier Reef, right? Because we get quite clearer skies at a particular time, let's say, and we get more solar radiation, and that's when they bleach. And then in another year, a La Nina happened, and we had bleaching. And then all the media was saying, well, it must be climate change, right? Because now we're having coral bleaching in La Nina when it should be raining over here. But what she did then was try to pull that particular event apart and was able to show that, in fact, when a Madden Julian oscillation came through and we were in the dry part of the eight-phase cycle, the clouds opened up, and that's when the bleaching actually happened. So this is a more sort of a dynamical approach to essentially understanding changes that we might just assume as something else. This is my colleague again, Alistair Hobday, and all I really want to say about this slide is a very busy slide, and I'm conscious that we're really now at almost 50 minutes. I think we started at 5 past, so 45 minutes. Just that you can use, like, if you like, archetypes. This is, again, if you like, the drivers paper that shows us the type of pattern that we would have during an El Nino. We knew that an El Nino was coming on, okay? And so, in effect, we put out, if you like, an archetypal forecast of where we think marine heat waves are going to be a problem, and tried to inform stakeholders of how they might best manage this, right? So it's like providing information to the world to do that. WA, Western Australia here, we expect, because of the El Nino coming on, probably unlikely to have problems, but over here, in the Indian Ocean and along here, could be really problematic. So that ended up getting published in Nature as a comment. And then there was an analysis undertaken after that the following year of those countries that in effect responded to that either positively or negatively or what they had. The other thing that we had was the CLEX. This is the ARC Centre of Excellence the Climate Extremes Workshop in 2023. We had a group of people together there. Some of them you may know. There's Antonietta Capotondi, for example. Min Steng's there, Alistair Hills, and so on. We got together and we planned out a few papers. One was particularly here led by Claire Spillman, who works for the Bureau of Meteorology. She works actively with Alistair Hobday, trying to put out forecasts for people, for stakeholders to understand what the marine heat waves are looking like for the seasonal forecast, a month, 2 months, 3 months in advance, and therefore what a good marine heat wave forecast might look like. That was published in Progress in Oceanography. There's another paper that should be coming out shortly, hopefully, looking at subsurface marine heat waves and what they look like, trying to provide some characterization of the types of marine heat waves, so almost like typology, putting the lid on subsurface. And then another original OUC 2+2 program student who did honours with me and then has recently done a postdoc with me, Didier Giles. He's been working with me on trying to look at more of an object approach, let's say, of marine heat waves. So you can see that these are evolving here. These are blobs, they evolve, and they're trying to understand the time and space evolution of those marine heat waves and how they are connected to the drivers dynamically, rather than looking in a fixed box and doing heat budget analysis locally. I think I'm very close to the end now. Okay. So this piece of work was done with also with stakeholders. In Tasmania, there's an important oyster, abalone, and Atlantic salmon industry. Okay, so the abalone are wild, and in fact, I don't know whether you know this, but 25% of the world's wild abalone comes from Tasmania, our little island south. Oyster is farmed and salmon are farmed, which is Atlantic salmon. The idea here was to try and understand under climate change how problematic it would be for these particular growers of oyster and so on. And the 2015-16 event, this case study event, was seen as the informant to that. So you can see here in a particular box region, we might have 19.5 degrees, which is very, very warm for these waters, about 40 days in that year. Whereas previously, we'd never seen anything like that, right? So how problematic was this? Well, it obviously had impact. And that 19.5 degrees was informed by stakeholders, so working with those stakeholders to understand that. I don't want too far. Okay. So under a low emission scenario, you can see that there, we want to see how often a 2015-16 event that had 40 days or more would happen with 2019.5 degrees. And then here's the high emission scenario, 8.5. And it turns out from that analysis, based on the spread across a multi-model ensemble, you can see that it turns out that by 2050, let's say, there's about a 50% chance, or 1 in every 2 years, of such an event happening in Tasmania, and under a low emission scenario, about 1 in 5 years. Another student working with me at the moment, John Riley, is trying to do ultra high resolution modelling using the new Australian Community Climate Earth System Simulator Access model, representing it here in this box here, okay, to try and understand just the more coastal region. So our focus now, I guess this is part of the abstract, is that we're really starting to try and focus more towards the coast, where the impacts are particularly large. This little model simulation just shows the difference is the observation. This is much coarser. In fact, it turns out the observations are much coarser at 25 kilometres. Here's a global model, but here's the regional model at 3 kilometres. So it's a 1/30th degree simulation running down the coast, just showing how the heat actually gets onto the shelf. So around Tasmania there and goes around the bottom. But the information that comes out of this is we start to learn something about the type of way that you can inject heat onto the coast. And it turns out here, this is just a picture, I think, of the flow lines. But you can see here where you've got let's say a cyclonic eddy and an anticyclonic eddy, where this one is further north. This is a mechanism then for injecting heat onto the shelf, right? So, and that's what's happened here. Here's a marine heat wave temperature anomaly that gets injected onto the shelf. So we're starting to understand now the type of mechanisms that might get warm water, let's say, up an estuary or onto the shelf. So now, just to finish off, this is the direction that we want to go. Here's our region now. Here's the Australian current that separates away from the coast, and this is the extension region. So in this particular project, which is part of the National Environmental Science Program, here's this modelling configuration that's set up by John Riley and others. We're using higher resolution models of, here's the 2 kilometre model, but this TASI model here, prepared by CSIRO, goes down to just a couple of 100 metres, and it goes right up into the estuary here, Derwent estuary and the Huon estuary. And so what we're hoping to do is to be able to get down to scales that are really important now for stakeholders to make decisions, but mainly focused on the hazard here. So we're trying to generate an overall hazard baseline understanding of our particular region. And that's where I'll leave it. And thank you for listening. I'm happy to take questions.
Thank you very much for your excellent talk, and I think I was here working now, learning about the exploring, understanding, everything. Right? Any questions and comments? Yeah. Yeah.
So that's a good question, right? So the thing that was one thing that we wrestled with early on in the piece. So El Nino, it obviously comes from time to time. La Nina comes from time to time. And it's part of the variability, right? Part of the natural variability. Under this definition that we apply, we think about the top 10% done. So even an El Nino event can be a marine heat wave if it's in the top 10%. So I think that's the short story, right? You know, the Galapagos Islands, let's say, might be experiencing El Nino quite a lot, and they might be quite adapted to those conditions. But this top 10 percentile is really the top 10 percentile based on a baseline climatology. Now, how you deal with that, there's a whole nother talk that I could give on baselines, and that's something that we're trying to understand over time. How species can potentially adapt, right? So you do a fixed baseline and you don't know over time how quickly species might adapt. So, there was a bit of a debate in the literature, I don't know whether you saw it, about that we really should shift our baseline, take it away for dynamic people in the room, to try and understand the variability around that baseline, shifting baseline. But the reality is the heat's actually changing, and we don't know how fast the species are going to adapt, right? So I'd probably departing from your question, but the point that I just want to make is, if you know how fast your species can adapt, then you can decide much better how you fix your baseline. So in the El Nino case, we're still really in a fixed baseline case, still caring about the top 10 percentile. And in any region, let's say in that cold tongue region where it will get really, really, really hot, like let's say the 2015-16 El Nino, which of course Professor Santoso can tell you all about, is very, very extreme and would be seen as a marine heat wave condition and potentially detrimental.
So if we separate the two types of relativity, one is prolonged, is very long term,
Yeah.
like energy
Yeah.
more than at least 60 months or even 1 year. So we may focus on two types. One is very long term,
Yeah.
very short term,
Yeah.
maybe less than 3 months. But in time.
Yeah. Yeah.
This way can separate the.
Yes, that's true. That's
Yeah.
true. Yeah, exactly. Yeah. Thank you. Yeah, thank you for your question.
Okay, okay. The
Hello.
thank you.
Yeah.
Is more like debate. I was always wondering that why is coffee weak? It's not something there just don't too much dynamics like waves.
No. Because it's just part of the language of atmospheric heat waves. Been around forever, right? They've always been called heat waves. So you're right, it's not a wave like that,
Yeah.
but it's just a terminology for something that's followed, right? Yeah. So we've just stuck with the language. It's not a wave like a duck.
Yeah.
It's just a prolonged ocean temperature extreme. And it's consistent with the atmospheric like, yeah. So we need to tell that as well, I think. That's what gets that way.
Yeah. But hypothetically weak because we can say that the center of the Mercury superheats from.
Yes, can
Yeah, this is like wave
Yeah.
dynamic.
be.
The rock wave
Can
can
be.
cause.
Yeah.
Mercury.
Yeah.
Yeah.
Yeah. You could have a wave number
Yeah.
or something in the Southern Ocean, right? And you see these blobs just moving along.
Yeah.
In that case, it'd be more like
Yeah.
a wave that you're thinking about. Yeah. We've had this discussion before, don't you worry. Yeah.
So then, single is a big top. So you look at it,
Yeah, we do that too. Yeah, that's a good point. So cumulative intensity is just the interval of intensity and duration. It's together. So in terms of impact, often we look at the cumulative intensity indeed. So it's the integral of both together. And when you combine that, because I think from impact studies, this is really important. I think one of the things that's really important is trying to understand, if you like, the morphology of the of the marine feeder. You know, like if you go to the gymnasium or something, you pedal really hard for a short time, that might be more stressful on your body and generate more, you know, work than if you just do it slowly for a long time, right? So what about if it's like sharp, up, then down, then flat, then up? So there's complicated ways that you can think about how much stress can be on different species. I think we're just beginning to understand that right at the beginning. There's a lot of opportunity.
The one hand is long, long,
Yeah,
and other hand is kind of dark or get dark.
yeah. I think these things require a lot more data and maybe more experimental, you know, experiments. So, you know, my other student, one of my students, Darren Hong, who's not there. Oh, yes, he is, the second one on the left there. He's just been looking at the stress of marine heat waves on snails. So he went to Canada, on the little snails. He went off Canada to see Professor Chris Harley at the University of British Columbia. They went and collected snails. They did tank experiments for like, I think it was 2 months or something, and trying to understand under different conditions and different baselines how they will respond. But there's a lot of work going on in that space and a lot of opportunity. And we don't have the answers yet, you know, for exactly how long it is, right? For example, in Tasmania, that 2015-16 event is the first incident of what we call Pacific oyster mortality syndrome. It generated a black spot on the oyster, and within 24 hours, the oysters died. But they were no good anymore, right? And that was an 8-month event, and it was 3 degrees above normal for a lot of that time. Well, we know that didn't do it any good. But whether a 4-month event would be enough, I don't think we have the answer to that. Right? That's all. But I mean, clearly it's a virus, right? The Pacific oyster mortality syndrome is a type of virus. So the temperature didn't cause the virus. The virus must be just there latent, and the temperature is just the stressor that sets it off. Yeah. No. There's no surprise there. Yeah. Okay, I can point you to a paper. There's a paper led by Katie Smith, and it was published on baselines and why baseline matters. And it gives you advice on the types of conditions that marine heat waves, where you might remove trends. It's a matter of choice at the end of the day, right? If you're a dynamicist and you want to see the extremes on a trend, then you remove the trend. But if you're interested in actually impact and you don't know about adaptation, then you might not choose to remove the trend, because the adaptation of the species is just going to be, you know, it's a different problem. It's a different problem. Yeah.
It's really not like,
No, it's not the type. No.
I think it
I don't
is.
think we're claiming it's a surprise. but it, yeah. Yeah. Yeah, that's right. Yeah. But again, it's about informing.
Yeah.
It's about
Yeah.
the information that you want to get. Right. The problem with what you say, and it's a really interesting point, and it has been debated, and there is a debate in the literature. You can go and read it. Is that you remove the trend, and then the message to stakeholders and the things that the media jump on is that the marine heat waves are getting better. Right? You remove the trend and marine heat waves aren't getting worse. So you've got to be careful about the messaging. There's a lot about information and trying to inform people appropriately. IPCC has adopted the role not to remove trend. They shift the baseline every 10 years. That's what the WMO do, right? So I think consistent with that process. But really you can do, you can go either way. If you're interested in the dynamics and the variability of the trend, then you should remove the trend. Does that make sense? Yeah, and I can give you the paper too that you can read. Yeah.
The other criteria. Common anesthetic. Okay. I look at the result of
I think because we didn't do it in the CI zone. I think that is the answer to your question. It's a very tricky zone because the CI zone is hard to get a baseline pharmacology against which to test marine heat waves. And you're right, obviously the Arctic is just getting crazy. But I think the cutoff for the analysis might have been just inside the CI zone, 30, 60 degrees north to south. So we didn't analyze that. Oh yes, and there are people doing that. Yeah, that's right. They are. Yeah, but we have not been. Oh, I think it's a bit scary because it's going to go like this, right? Yeah, because it's a positive feedback. Positive and negative sense. There's more sea ice melts, it's just going to get hotter and hotter very fast. Yeah. But there are people working on Arctic stuff for sure, and people working on Antarctic for it.
Yeah, we have. I think now. Oh.
Pleasure. Thank you. That's exactly right.
So
Yeah.
I'm wondering what you.
Yeah, I think that it's something that there's a lot of work going on at the moment, right? And I didn't really touch on that here. I mentioned that there's that Neil Malone paper that is being done. And I've also got a student, Shubin Jung, who's another one from overseas, working with Alexander Burnley on looking at subsurface. That work is trying to understand, firstly, the point is trying to understand, getting heat into the ocean is tricky, right? It's very hard. And you can do it dynamically by just heat moving, ice signals up and down, but you can also do it through spikes, where you get a long ice signal flow. So they're the two ways that it's been examined. In answer to your question in terms of the biology, it's hard to know, I think if you're something that's fixed on the ocean floor, you can't go anywhere, then you're going to hurt, right? It's going to be harmful. But if you're something that can swim away, maybe, and there are papers starting to be on there. If you're a if you're something that doesn't move much, but you're sitting on a dynamically one where it's hyperthermal movement steam, maybe you don't feel the heat. But if you're actually getting heat down through a spice mechanism, then maybe it could be more detrimental. So I think it depends on the mechanism, and it probably also depends on whether you can swim or you can't swim too. But I think, again, early days to understand that, which is why I think this area is really interesting from an interdisciplinary point of view, right? Because there's a lot of ecology stuff to be understood as well. Does that sort of answer your question? Yeah, somewhat.
Please correct the Tanzala.
Yes, I know. Yeah. Well, I know you now, but I know your name. Nice to meet you.
Thank you.
Yeah. Yes, it's a climate change hotspot. Look. So the Western Boundary Current regions around the world, there was a paper by Li Qin and others, some 10 years ago or so, and they do initiatives looking at the Western Boundary Current changes. And so they're all, in effect, pushing the, so this is a climate change, more of a climate change signal, pushing the extension regions, getting them warmer and warmer and warmer. But in answer to your question about that region as a hotspot, that's the climate change hotspot, but it's also strongly influenced by the advection of the East Australian Current. And also, it's also a region where we get these blocking tides. They come across and then they block and they sit for a while, peak, and then they basically move on then. So, yeah, there's two kind of key processes that are affecting that region. But yeah, I mean, the thing is as the ocean keeps warming up, it's going to be more and more of a problem. How fast it's happening is serious concern. I think the region of Tasmania is warming 2 to 3 times the global average rate is the number.
Okay, thank you very much. I think if you other students have questions, please email me.
Yes, please. Yeah, send me an email.
Yeah.
Can you send me an email? I'll send you the paper.
So when I come to this part, so some statistics, you include on-site part.
Yeah.
We also adopt the online,
Oh, yes.
live and streaming platform.
Oh, yeah.
There are 15,000 orders.
15,000. Wow.
Very large.
That was a big
You
I'm glad you're telling me now. I'm glad you're telling me now.
Okay.
And not before.
So let's thank Nilo once again for sharing his appetite to us today.
Yes, thank you.
And the gesture of our appreciation,
Yeah.
I will present a gift
Oh,
for
thank
you.
you very much. You're such a
Okay, this is the this is a beautiful seashell, representing the famous landmark of Freedom. Mayford Square. Okay? Yeah. Yeah, thank you very much. Thank you very much. Thank you for your family. Thank you.
I know. Now for the teacher. Oh, you need that email. It's in the Oh, yes. Really good. You're doing your PhD? Yeah.
And my profit are you?
Oh, right, great. Oh, hi, Joanna. How are you? Yeah. You happy? Yeah, yeah. The one part. Yeah. Yeah. Nearly 2. Yeah, that's right. I'm just about to leave, but I've got to go teach for 2 hours.
Oh, yeah.
From 3:30.